We begin our story not in the distant, glittering star fields of the cosmos, but right here, in the familiar air above our heads. For most of human history, outer space was a realm of gods and myths, a celestial tapestry hung far beyond our reach. We saw it as a place fundamentally separate from our own, an inaccessible domain of shimmering lights and profound darkness. Yet, the truth is far more intimate. The great final frontier does not begin in some remote corner of the galaxy. It begins in a place so close you could travel there in the time it takes to drive to the next city. It is a journey not across a vast ocean, but straight up into the deepening blue of our own sky. This journey has a destination, a recognized threshold where the sky ends and space begins. While there is no physical signpost, international convention largely accepts an invisible boundary known as the Kármán line, an imaginary circle drawn 100 kilometers, or roughly 62 miles, above the sea. It owes its name to Theodor von Kármán, a brilliant Hungarian-American engineer and physicist who, in the mid-20th century, first calculated the altitude at which our atmosphere becomes too thin to support conventional flight. At this height, a vehicle would have to travel faster than orbital velocity to generate enough aerodynamic lift to stay aloft. It is at this point that the laws of aeronautics give way to the laws of astronautics. We find that the universe is full of these fascinating details and the remarkable people who uncovered them. And to ensure you are notified of our future stories exploring these scientific chronicles, we invite you to subscribe. Imagine ascending towards this line from the ground. The first 15 kilometers, about 9 miles, take you through the troposphere and stratosphere, home to our weather, our clouds, and the jet streams that circle the globe. As you climb higher, the air, once a dense and life-giving medium, begins to thin profoundly. The rich, vibrant blue of the sky, a color created by sunlight scattering off air molecules, slowly darkens, shifting through shades of indigo and violet. You rise above the highest clouds and the flight paths of commercial airliners, entering a silent, serene world where the pull of Earth's gravity is still overwhelmingly strong. Yet the substance of its atmosphere has all but vanished into the void. Crossing the Kármán line is not a dramatic jolt, but a silent, momentous transition. Below you, Earth is a vast, curving panorama, its atmosphere a paper-thin, luminous shell. Above, the sun shines not in a blue sky, but as a brilliant, sharp star set against an endless, velvety blackness. A darkness now filled with the unwavering light of countless other suns. You are no longer flying through the air, but falling around the world, an astronaut in the truest sense of the word. From this vantage point, just beyond the edge of our world, we can begin to comprehend the sheer scale and mystery of what lies ahead. the boundless and beautiful expanse we call outer space. This boundless expanse, however, is deeply misunderstood, for its most defining characteristic in the human imagination is a profound and absolute emptiness. We call it the void, a word that conjures images of utter nothingness, a perfect vacuum stretching infinitely in all directions. And in a sense, this is true. The difference in density between the air at sea level and the interplanetary medium is more extreme than the difference between that same air and the densest solid gold. Here on Earth, each cubic centimeter of air, a space about the size of a sugar cube, is teeming with quintillions of molecules. Yet in the space between planets, that same volume might hold only 5 or 10 atoms. It is a vacuum far more perfect than any we can create in our most advanced laboratories on Earth. This near total absence of matter has profound consequences. It is why there is no sound in space, as sound requires a medium to travel through. It is also why temperature behaves so strangely. An object in sunlight can be heated to hundreds of degrees, while its shaded side plummets to a cryogenic cold, because there is no air to distribute the heat. Astronauts returning from spacewalks have even reported a peculiar smell, a faint, metallic, and acrid scent, like burnt steak or hot metal, thought to be the odor of highly energetic particles reacting with the fabric of their suits, a ghostly scent of the void itself. But this vacuum is not true nothingness. It is instead a canvas, and it is filled with a rich and complex tapestry of energy and matter, most of it invisible to our eyes. The vast majority of the ordinary, visible matter in the universe exists in a state that is rare on Earth, a state known as plasma. This is the fourth state of matter, beyond solid, liquid, and gas, created when a gas becomes so hot that its atoms are torn apart, leaving a swirling sea of charged particles, ions, and electrons. Our own sun is a giant ball of plasma, and it is constantly breathing this substance out into the solar system in a relentless stream called the solar wind. This solar wind streams outwards at astonishing speeds, typically around 400 kilometers per second, which is nearly 900,000 miles per hour, bathing every planet, moon, and asteroid in its flow. When this river of charged particles interacts with a planet's magnetic field and atmosphere, it creates the beautiful, shimmering curtains of light we call the aurora. The long, elegant tails of comets are also shaped by this wind, always pointing away from the sun, no matter which direction the comet is traveling. This plasma, thinning with distance, fills the space between the planets, and in an even more rarefied form, it fills the immense gulfs between the stars, where it is known as the interstellar medium. And on the grandest scales, an incredibly tenuous, hot plasma pervades the space between galaxies, forming the intergalactic medium, a ghostly web connecting the great cosmic cities of stars. Even more pervasive than this plasma is a faint, persistent glow of energy that fills the entire universe, a whisper from the very beginning of time. This is the cosmic microwave background radiation, the oldest light in existence, an echo of the Big Bang itself. Its discovery is a wonderful story of scientific serendipity. In the year 1965, two American radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna in New Jersey, trying to hunt for radio waves from the Milky Way. They were plagued by a persistent, faint, and uniform hiss in their readings, a noise that came from every direction in the sky, day and night, season after season. They checked their equipment, rewired their systems, and even cleaned out pigeon droppings from inside the antenna, suspecting it might be a source of thermal noise, but the hiss remained. At the same time, a team of physicists at nearby Princeton University, led by Robert Dicke, had theorized that if the universe began in a hot, dense state, it should have left behind a cooled remnant glow, and they were building an experiment to find it. When the two groups learned of each other's work, the truth became clear. The hiss in the antenna was not a malfunction. It was the sound of creation. It was the afterglow of the universe's birth, a flood of light released when the cosmos was just 380,000 years old, now cooled and stretched by cosmic expansion into the microwave portion of the spectrum. This cosmic hum corresponds to a temperature of just 2.73 degrees above absolute zero, a frigid minus 270 degrees Celsius, which is about minus 454 degrees Fahrenheit, the baseline temperature of the universe itself, the cold that remains when you have fled from every star. Beyond this ancient light, space is also coursing with travelers of a more substantial kind. The void is crisscrossed by cosmic rays, which, despite their name, are not a form of light, but are physical particles, mostly protons and atomic nuclei, that have been accelerated to tremendous energies by some of the most violent events in the cosmos, such as exploding stars called supernova. These particles travel at speeds just shy of the speed of light, carrying an incredible punch. When they strike the upper atmosphere of Earth, they shatter atoms, creating a shower of secondary particles. While our atmosphere and magnetic field protect us from the worst of this bombardment, it remains a significant hazard for astronauts and unshielded electronics in space. And then there are the most elusive particles of all, neutrinos. These are ethereal, ghost-like particles produced in the nuclear furnaces of stars and in violent cosmic explosions. They have almost no mass and no electric charge, and as a result, they barely interact with other matter at all. Every second of every day, hundreds of billions of neutrinos streaming from our own sun pass harmlessly through your body, through your bones and your blood, and continue on through the entire planet Earth as if it were not even there. To them, a wall of lead several light years thick would be as transparent as a clean window pane is to light. These countless, silent particles, along with cosmic rays, pervasive magnetic fields, and drifting dust grains, complete the picture of a space that is not empty, but is instead a dynamic, active, and surprisingly full environment, a physical medium that carries the history of the cosmos from its fiery birth to the present day. And yet, this physical medium, this surprisingly full void, stands in stark contrast to the dense, life-sustaining medium of our own atmosphere, creating a fundamental question that has puzzled scientists and lawyers for decades. Where, precisely, does one end and the other begin? The desire for a clear line in the sky is a deeply human one, a need to demarcate our world from the great beyond. But the universe rarely deals in such certainties. The transition from Earth to space is not a hard border, but a delicate and graceful gradient, a slow fading of our world into the cosmos. To truly understand the challenge of drawing this line, we must first journey through the layers of the atmospheric ocean, a voyage upward from the ground we stand on. Our journey begins in the troposphere, the lowest and densest layer, a turbulent, churning engine that contains as 80% of the atmosphere's mass and nearly all of its water vapor. It is the realm of clouds, of storms, of the air we breathe. Extending upwards for an average of 12 kilometers, or about 7 miles, this is where our weather is born. As we ascend through it, the temperature steadily drops, a familiar sensation to anyone who has seen snow on a mountaintop. Then, at the top of the troposphere, we cross a boundary called the tropopause and enter the stratosphere. Here, the world changes. The air is thin and dry, and the turbulent weather of the world below is left behind. This is a realm of immense stability, where commercial airliners cruise on steady currents to avoid the turmoil of the troposphere. And here, a strange thing happens. The temperature begins to rise. This warming is caused by the presence of the ozone layer, a fragile shield of molecules that absorbs the sun's harmful ultraviolet radiation, warming the stratosphere and making life on the surface possible. This layer extends to an altitude of about 50 kilometers, or 31 miles, where we find another boundary, the stratopause. Beyond the stratopause lies the mesosphere, a layer that was largely a mystery for much of the 20th century, too high for balloons and too low for satellites. It extends up to about 85 kilometers, or 53 miles. And it is here that the temperature begins to fall once again, reaching the coldest points in the entire atmosphere, plunging as low as minus 100 degrees Celsius, or minus 148 degrees Fahrenheit. The air here is incredibly thin, yet it is thick enough to create friction for the millions of meteors that enter our atmosphere every day. When we see a shooting star streak across the night sky, we are witnessing a tiny speck of cosmic dust burning up in the mesosphere, a final, fleeting flare of light. In this layer, at the very edge of the polar nights, a beautiful and ethereal phenomenon can occur: noctilucent, or night shining, clouds. These are impossibly thin wisps of ice crystals that form on fine dust particles, so high that they catch the sunlight long after the sun has set for observers on the ground, glowing with a ghostly, electric blue light against the deepening twilight. Above the mesosphere, we cross the mesopause and enter the final major layer, the thermosphere. This vast region extends from around 85 kilometers up to 600 kilometers, or about 375 miles, and beyond. Here, the concept of air as we know it ceases to have meaning. The gas particles are so few and far between that they can travel for kilometers without colliding. Yet these individual particles, bombarded by the sun's most energetic radiation, are heated to extreme temperatures, potentially reaching 2,000 degrees Celsius, which is over 3,600 degrees Fahrenheit. An ordinary thermometer here, however, would register extreme cold because the density is so low that there are not enough particles to transfer that heat. It is a world of extreme paradox, and it is here, in this near vacuum, that the brilliant spectacle of the aurora unfolds, and where the International Space Station traces its silent, orbital path. Finally, above the thermosphere lies the exosphere, the final frontier of our atmosphere, where the air is so thin it is indistinguishable from the interplanetary medium. It has no clear upper boundary, simply fading away into the vacuum of space, with the outermost, lightest atoms of hydrogen and helium slowly leaking away from Earth's gravitational grasp. This journey upward reveals the central problem. Our atmosphere does not end, it dissolves. There is no wall, no ceiling, only a gradual dispersal into nothingness. Faced with this ambiguity, humanity has had to invent a boundary. The most widely accepted of these is the Kármán line, the conceptual border at 100 kilometers, or 62 miles, that we met in our introduction. Its logic, as formulated by Theodor von Kármán, is one of elegant physics. He recognized that an object's ability to fly depends on two forces: aerodynamic lift, generated by air moving over wings, and centrifugal force, the outward push from turning, which in this case is orbiting the Earth. As an aircraft goes higher, the air gets thinner, so it must go faster to generate the same amount of lift. Von Kármán calculated that at a certain altitude, the speed needed to create enough lift to support the vehicle would become so high that it would equal the speed needed to enter a stable orbit. At this point, the air is effectively useless for flight. You are no longer flying. you are orbiting. This altitude, where astronautics takes over from aeronautics, is the Kármán line. The Fédération Aéronautique Internationale, the world governing body for air sports and aeronautical records, adopted this 100-kilometer definition in the 1960s, and it has since become the common standard for differentiating a pilot from an astronaut. However, this is not the only definition. The United States, for instance, has never officially adopted the Kármán line. NASA, the U.S. Air Force, and the Federal Aviation Administration award astronaut wings to anyone who flies above an altitude of 50 miles, which is approximately 80 kilometers. This alternative boundary is not arbitrary. It corresponds roughly to the mesopause, the top of the mesosphere, and it is the altitude where the atmospheric drag on a re-entering spacecraft starts to become noticeable. This discrepancy creates a curious situation. An individual could launch to an altitude of 90 kilometers, or 56 miles, and be considered an astronaut by the United States government, yet not have officially reached outer space by the common international definition. This is more than just a matter of scientific debate. It bleeds into the complex world of international law. The foundational document governing our activities in space is the Outer Space Treaty, signed in 1967. This landmark agreement declares space to be the province of all humankind, free for exploration and use by all nations, and explicitly forbids any country from claiming sovereignty over celestial bodies. It is the reason that nations can freely operate satellites that orbit over the entire globe without needing permission to cross borders. But for all its importance, the treaty has one glaring omission. It never actually defines where airspace, which is sovereign national territory, ends and outer space begins. This lack of a formal, legally binding demarcation, known in legal circles as the delimitation problem, creates a vast and increasingly relevant gray area. As new technologies, like hypersonic vehicles and advanced suborbital tourist craft, begin to operate in these upper reaches of the atmosphere, the question of which laws apply becomes critically important. Is a vehicle traveling at 95 kilometers altitude flying through a nation's sovereign airspace? Or is it passing through international space? The answer has profound implications for commerce, security, and the very concept of national borders in the 21st century. The simple act of drawing a line in the sky is, it turns out, one of the great unfinished tasks of the space age, a testament to the fact that even as we reach for the stars, we are still grappling with the fundamental definitions of the world right above our own. Leaving behind these earthly debates over invisible lines, we cross the threshold into our local cosmic neighborhood, a realm governed not by the gentle pull of our planet, but by the overwhelming, incandescent power of a star, our sun. This is the heart of our solar system, a colossal sphere of incandescent plasma so vast that you could fit 1.3 million Earths inside it. It is not a solid body, but a raging nuclear furnace, fusing hundreds of millions of tons of hydrogen into helium every second in its core, where temperatures reach a staggering 15 million degrees Celsius, or 27 million degrees Fahrenheit. This process unleashes a torrent of energy that radiates outward, a tide of light and heat that has powered our world for more than 4 billion years. The sun is the anchor of our system, containing more than 99.8% of all its mass, its immense gravity holding every planet, moon, asteroid, and comet in a precise and predictable dance. From this fiery center, we begin our own journey outward, a grand tour of the worlds that populate our cosmic home. Our first stop is Mercury, the innermost and smallest of the planets, a world locked in a brutal embrace with the sun. It is a place of savage extremes, with almost no atmosphere to trap heat or distribute it. The side of Mercury facing the sun scorches at temperatures of 430 degrees Celsius, or 800 degrees Fahrenheit, hot enough to melt lead, while on the night side, the temperature plummets to a cryogenic minus 180 degrees Celsius, or minus 290 degrees Fahrenheit. Its surface is a testament to a violent past, pockmarked with craters from eons of bombardment, closely resembling our own moon. For decades, it was thought to be a simple, geologically dead rock. But the Messenger spacecraft, which orbited the planet in the early 21st century, revealed a world of surprises. It discovered that Mercury has a massive metallic core that generates a weak but significant magnetic field. And even more astonishingly, it found evidence of water ice tucked away in the permanent shadows of craters near its poles, a sliver of frost surviving in a world of fire. Moving outward, we next encounter Venus, a planet often called Earth's twin due to its similar size and composition. But if it is our twin, it is a twisted and malevolent one. Venus is a vision of hell, shrouded in a thick, toxic atmosphere of carbon dioxide and clouds of sulfuric acid. This dense blanket of gas has created a runaway greenhouse effect, trapping heat so efficiently that the surface temperature is a uniform and blistering 465 degrees Celsius, or 870 degrees Fahrenheit, making it the hottest planet in the solar system, even hotter than Mercury. The atmospheric pressure at the surface is over 90 times that of Earth, equivalent to the crushing weight of being 1 kilometer, or over half a mile, deep in our oceans. Several Soviet Venera probes in the 1970s and 80s managed to land on this hostile surface, transmitting images of a bleak, orange-tinted landscape of volcanic rock for a few precious minutes before being crushed and cooked into silence. Beyond this inferno, we pass the orbit of our own planet, Earth, a unique and fragile jewel of blue oceans, white clouds, and green continents, a world whose position in the so-called habitable zone has allowed liquid water to persist, and complex life to flourish. Our journey continues to Mars, the red planet, a world that has captivated human imagination for centuries as a potential abode for life. Today, it is a cold, desert world, with a thin carbon dioxide atmosphere less than 1% the density of Earth's. This thin air means it cannot retain much heat, leading to dramatic temperature swings and vast, planet-engulfing dust storms. Yet, everywhere we look on Mars, we see the ghosts of a different past. The robotic eyes of rovers like Curiosity and Perseverance have shown us ancient riverbeds, dried-up deltas, and minerals that could only have formed in the presence of water. It is a world that was once warmer and wetter, with a thicker atmosphere, and perhaps even shallow seas. Today, its water is locked away in its polar ice caps and frozen as permafrost beneath the rusty, iron-rich soil. Mars has two tiny, potato-shaped moons, Phobos and Deimos, likely captured asteroids that now circle the planet closely, their names meaning fear and dread, fitting companions for the world named after the Roman god of war. Beyond Mars, the character of the solar system changes. We cross a vast, cold, and largely empty expanse known as the asteroid belt. This is not the crowded, chaotic field of tumbling rocks often depicted in science fiction. In reality, the asteroids are so far apart that a spacecraft flying through the belt has an almost zero chance of hitting one by accident. It is a region of cosmic rubble, the leftover material from the formation of the solar system that was prevented from coalescing into a planet by the immense gravitational influence of our next destination. Within this belt reside Ceres, the largest of the asteroids and a designated dwarf planet, a world of rock and ice with mysterious bright spots of salt deposits on its surface. Emerging from the asteroid belt, we enter the realm of the giants, and first among them is the undisputed king of the planets, Jupiter. This is a world on a scale that is difficult to comprehend. It is so large that all the other planets in the solar system could fit comfortably inside it. Jupiter is a gas giant, composed mostly of hydrogen and helium, with no solid surface to stand on. What we see are its swirling, multicolored cloud tops, organized into vibrant bands and zones by ferocious winds that can reach speeds of over 600 kilometers per hour, nearly 400 miles per hour. Its most famous feature, the Great Red Spot, is a colossal anticyclonic storm wider than the entire Earth that has been raging for at least 400 years. Jupiter is also a system in miniature, orbited by nearly 100 moons. The four largest, known as the Galilean moons, are worlds in their own right. There is Io, the most volcanically active body in the solar system, its surface constantly repaved by sulfurous eruptions. There is Europa, covered in a shell of water ice that may hide a vast, global liquid ocean, making it one of the most promising places to search for extraterrestrial life. Ganymede, the largest moon in the entire solar system, is bigger than the planet Mercury and has its own magnetic field. And finally, there is Callisto, a heavily cratered ancient world that may also harbor a subsurface ocean. Continuing our journey, we arrive at Saturn, the jewel of the solar system, a planet whose beauty has enchanted observers for centuries. While Saturn is another gas giant, similar in composition to Jupiter, it is distinguished by its breathtaking system of rings. These are not solid structures, but a vast, shimmering disk composed of countless billions of individual particles of water, ice, and rock, ranging in size from grains of dust to the size of a house. This intricate system stretches for thousands of kilometers, but is, in most places, only a few tens of meters thick. Saturn also hosts a fascinating collection of moons, including the enigmatic Titan, the only moon in the solar system with a thick atmosphere, a dense, nitrogen-rich haze that shrouds a world of methane rivers, lakes, and seas. Another moon, Enceladus, is a small, icy world that sprays plumes of water vapor and ice particles from deep fissures in its southern polar region. Another tantalizing hint of a life-friendly ocean hidden beneath the ice. Our voyage now takes us into the deep, frozen outer reaches. We come to Uranus, the seventh planet, an ice giant tipped on its side. Its axis is tilted at an angle of 98 degrees, meaning it essentially orbits the Sun on its side, rolling through its 84-year orbit, with its poles pointing where other planets have their equators. This bizarre orientation may be the result of a colossal impact with an Earth-sized object early in its history. Uranus is a serene, almost featureless world of pale cyan, its atmosphere a frigid mix of hydrogen, helium, and methane, which gives it its distinctive color. Finally, we reach the last of the recognized planets, Neptune, another ice giant, and a world of deep azure blue. It is the windiest planet in the solar system, with storms whipping through its upper atmosphere at speeds exceeding 2,000 kilometers per hour, or 1,200 miles per hour. When the Voyager, 2 spacecraft flew past in 1989, it imaged a large cyclonic storm dubbed the Great Dark Spot, similar to Jupiter's, though it had vanished when the Hubble Space Telescope looked years later. Neptune's largest moon, Triton, is a strange and wondrous place, orbiting the planet backwards in a retrograde orbit, suggesting it is a captured object from the farther reaches of the solar system. It is one of the coldest bodies ever measured, yet it is geologically active, with geysers of nitrogen gas erupting from its frozen surface. Beyond Neptune, we enter the third and final zone of our solar system, a vast, dark, and icy realm known as the Kuiper Belt. This is a donut-shaped ring of trillions of icy bodies, the frozen remnants of planetary formation. This is the home of Pluto, once considered the ninth planet, but now understood as the largest and most complex member of this distant family of worlds. The New Horizons mission, which flew past in 2015, revealed Pluto to be a world of stunning complexity, with vast plains of frozen nitrogen, towering mountains of water ice, and a thin, blue-tinted atmosphere. It is the king of the Kuiper Belt, a vibrant world presiding over a dark and silent kingdom. And even beyond this, surrounding our entire system like a vast, ghostly shell, lies the theoretical Oort cloud, a spherical swarm of trillions of comets, extending perhaps a quarter of the way to the next star. This is the final, tenuous frontier of the Sun's gravitational dominion, the last outpost of our cosmic neighborhood before the truly immense leap into interstellar space. This immense leap into interstellar space carries us beyond the last whispers of the Sun's influence and into a fundamentally new environment. For decades, we could only imagine this transition. But in the early 21st century, humanity's first emissaries, the twin Voyager spacecraft launched in 1977, physically crossed this boundary. They passed through a turbulent frontier known as the heliopause, the invisible bubble where the solar wind, that constant stream of particles from our sun, finally falters and is turned back by the gentle but persistent pressure of the interstellar medium. In 2012 and 2018, respectively, Voyager 1 and Voyager 2 went silent to the sun's breath and began to feel the wind of the stars. They detected a sharp increase in the density of cosmic rays and a dramatic drop in the solar particles, confirming they had left the cradle of their birth and entered the great ocean between the stars. It is a lonely, quiet, and profoundly dark place, filled with a tenuous mix of gas and dust that has drifted in this void for billions of years, the raw material from which future suns and worlds might one day be born. To chart these new, unimaginable distances, we require a new and grander yardstick, the light year. This is not a measure of time, but of distance, representing the length that a beam of light travels in one terrestrial year. Given that light moves at the ultimate cosmic speed limit, a staggering 300,000 kilometers per second, or roughly 186,000 miles per second, a single light year is an immense span, equivalent to nearly 9.5 trillion kilometers, or just under 6 trillion miles. The scale this unit reveals is humbling. The Oort cloud, that vast, theoretical sphere of comets marking the edge of our solar system, may extend over a light year, perhaps even 2, from our sun. But the very next star, a faint, small, and cool red dwarf named Proxima Centauri, is more than 4.2 light-years away. To put this into perspective, if our sun were the size of a grapefruit in London, Earth would be a grain of sand orbiting it from 15 meters, or about 50 feet, away. On this scale, the nearest grapefruit, Proxima Centauri would be in Moscow. Our fastest spacecraft, the Parker Solar Probe, traveling at its peak speed, would still take thousands of years to cover such a distance. Proxima Centauri is part of a triple star system, gravitationally bound to its two much larger and brighter companions, Alpha Centauri A and B, which orbit each other like a brilliant stellar pair. These two are much more like our own sun, and in recent years, our telescopes have confirmed that this nearest stellar system is not a barren wasteland. A planet, at least one, has been detected orbiting Proxima Centauri, a tantalizing hint that worlds are a common feature of the cosmic landscape. As we move through this interstellar space, we find that it is not uniformly empty. The interstellar medium, the rarefied gas and dust that fills the void, has a complex and beautiful geography. In some regions, it is incredibly thin, a near-perfect vacuum. In others, it gathers into vast, ethereal clouds known as nebulae, the celestial nurseries and graveyards of the stars. Some of these nebulae glow with a spectacular, vibrant light of their own. These are emission nebulae, like the famous Orion Nebula, a stellar nursery located some 1,300 light-years from Earth. Here, the intense ultraviolet radiation from hot, massive young stars embedded within the cloud energizes the surrounding hydrogen gas, causing it to fluoresce with a characteristic, beautiful, reddish glow. Within these glowing folds of gas and dust, gravity is slowly pulling material together into dense clumps, the protostars that will eventually ignite to become the next generation of suns. Other nebulae shine not with their own light, but with the reflected brilliance of nearby stars. These are reflection nebulae, and because the fine dust within them scatters blue light more effectively than red, they often appear as ghostly, luminous blue veils, like the delicate wisps surrounding the Pleiades star cluster. And then there are the dark nebulae, like the famous Horsehead Nebula, also in the constellation of Orion. These are clouds of gas and dust so dense and cold that they do not emit or reflect visible light at all. Instead, they appear as dark, imposing silhouettes, holes in the starry background. But in reality, they are obscuring the light of the stars behind them. They are not holes, but concentrations, the coldest and densest regions of interstellar space, places where the seeds of future star formation lie dormant in the deep, cosmic winter. All these stars, these stellar systems, these glowing and dark nebulae, are not scattered randomly through the cosmos. They are all individual citizens of a much grander structure, a colossal, rotating city of stars we call the Milky Way galaxy. This is our home island in the cosmic ocean, a vast barred spiral galaxy containing an estimated 200 to 400 billion stars. Our entire solar system is just one tiny, almost insignificant part of this structure. From our vantage point inside it, we cannot see its shape in its entirety, just as you cannot see the shape of a forest when you are standing among the trees. Instead, we see its light as a faint, milky band stretching across the night sky, the combined glow of billions of distant, unresolved stars in the galactic disk. This disk is the galaxy's most prominent feature, a flattened, spinning plane of stars and dust, about 100,000 light years in diameter, which is roughly 950 quadrillion kilometers, or about 600 quadrillion miles. This disk is not uniform, but is organized into several sweeping spiral arms, regions of higher density where star formation is most active. Our own sun resides in a smaller, partial arm known as the Orion Cygnus arm, about 27,000 light years from the galactic center. At the heart of the galaxy lies a dense, bright, elongated region of older, yellowish stars known as the central bar. And within this bar is the galactic core itself. Here, stars are packed together thousands of times more densely than in our own neighborhood, swarming around a gravitational anchor of unimaginable power, a supermassive black hole named Sagittarius A star, which has a mass more than 4 million times that of our sun. Surrounding this entire disk and central bulge is a vast, spherical, and much more sparsely populated region called the galactic halo, containing scattered ancient stars and mysterious globular clusters, dense, spherical swarms of hundreds of thousands of the galaxy's oldest stars. It is here, suspended in this vast, swirling city of suns, 2/3 of the way from its brilliant, chaotic center, that we make our home, looking out into the night and trying to comprehend the sheer scale of the island we inhabit before we dare to look for the shores of others. Looking out from our home among the swirling arms of this stellar city, the human spirit cannot help but wonder about the shores of others. For a long time, we believed our island was the entire universe. The faint, fuzzy patches of light we saw through our telescopes, the ones we called spiral nebula, were thought to be fledgling solar systems forming within our own Milky Way. But in the 1920s, a great debate raged in the astronomical community. Were these smudges of light local phenomena? Or were they, as some audaciously proposed, entire island universes in their own right, other galaxies as vast as our own, lying at unfathomable distances? The question was finally settled by the tireless work of an American astronomer named Edwin Hubble. Using the colossal 100-inch, or 2.5-meter, Hooker telescope at the Mount Wilson Observatory in California, Hubble painstakingly observed the largest of these spiral smudges, the Andromeda Nebula. He was searching for a specific type of star, a Cepheid variable, a celestial beacon, whose brightness rhythmically pulses over a period of days or weeks. Earlier, the astronomer Henrietta Swan Leavitt had made a revolutionary discovery. The longer a Cepheid's pulse period, the greater its true, intrinsic brightness. This relationship turned these stars into cosmic yardsticks. By measuring a Cepheid's pulsation period, you could know how bright it truly was. And by comparing that to how dim it appeared from Earth, you could calculate its distance with unprecedented accuracy. In 1924, Hubble found his prize, a Cepheid variable star in the outskirts of Andromeda. His calculations delivered a stunning verdict. The star, and by extension the entire nebula, was located nearly 1 million light-years away, a distance so vast it placed it far, far beyond the most generous estimates for the edge of the Milky Way. This was no cloud of gas within our galaxy. It was a sister city of stars, a sibling galaxy in the cosmic dark. In a single stroke, the known universe had expanded by a factor of hundreds, perhaps thousands. The shores of other islands were not just real. They were everywhere we looked. These islands, it turns out, are not solitary castaways in the cosmic ocean. They are social creatures, bound together by the invisible hand of gravity into families and communities. Our own Milky Way is part of a small, intimate gathering of more than 50 galaxies known as the Local Group. This group is dominated by its two largest members, our galaxy and the magnificent Andromeda Galaxy, which is slightly larger than our own and lies some 2.5 million light-years away, a distance of about 24 quintillion kilometers, which is 15 quintillion miles. Andromeda is the most distant object the unaided human eye can perceive, a faint, fuzzy patch of light in the autumn sky. The third major member is the smaller Triangulum Galaxy, another spiral. But the rest of the group consists of a swarm of smaller, fainter dwarf galaxies. Many of these are satellites, gravitationally enslaved to their larger hosts. Our Milky Way, for instance, is attended by several dozen of these diminutive companions, the most famous of which are the Large and Small Magellanic Clouds, two irregular galaxies visible from the southern hemisphere that look like detached fragments of the Milky Way itself. These galaxies come in a beautiful variety of forms. Beyond the majestic spirals like ours, there are colossal elliptical galaxies, which are vast, featureless, egg-shaped swarms of ancient, reddish stars, often found at the heart of much larger galactic congregations. Then there are the irregular galaxies, which, as their name suggests, have no defined shape at all. Their chaotic structures often the result of gravitational tugs of war with their neighbors. The members of our local group are locked in a complex gravitational dance, and this dance has a dramatic future. The great Andromeda Galaxy is not moving away from us, but hurtling towards us at a speed of about 110 kilometers per second, or nearly 250,000 miles per hour. In about 4.5 billion years, our two majestic spiral galaxies will begin a slow, graceful, and titanic collision, merging over hundreds of millions of years into a single, giant new elliptical galaxy, a future cosmic metropolis that some astronomers have already nicknamed Milkomeda. Just as stars gather into galaxies, galaxies themselves gather into even larger structures. Zooming out from our local neighborhood, we find that our local group is not isolated, but is, in fact, an outlying suburb of a much grander congregation, the Virgo cluster. Located about 54 million light-years away, this is the nearest large galaxy cluster to us, a teeming cosmic city containing well over 1,000 galaxies packed into a volume of space only a few million light-years across. At its heart lie several giant elliptical galaxies, cosmic behemoths that have grown to their enormous size by gravitationally consuming their smaller neighbors over billions of years. And this pattern repeats across the cosmos. Galaxy clusters are the great crossroads of the universe, the places where matter has most successfully accumulated. But even these are just nodes in an even larger pattern. Our local group, along with the Virgo cluster and about 100 other galaxy groups and clusters, are all part of a single, colossal supercluster, a filamentary structure of galaxies stretching across more than 500 million light-years of space. For many years, we called this the Virgo supercluster. But in 2014, astronomers redefined our cosmic address, realizing that we are part of an even grander entity they named the Laniakea supercluster. The name, from the Hawaiian language, means immense heaven, a fitting tribute to its scale. Laniakea is not a simple clump, but a sprawling network of galaxies, all flowing through space toward a common gravitational basin. A single point in the intergalactic medium, known as the Great Attractor, an enormous concentration of mass whose gravitational pull shapes the motion of 100,000 galaxies, including our own. We are not just adrift in space. We are a drop of water in a vast cosmic river, flowing along a filament of galaxies towards a mysterious, unseen destination. When we take our final step back, plotting the positions of millions of galaxies gleaned from massive sky surveys, the ultimate and most breathtaking structure of the universe reveals itself. On the very largest scales, the cosmos is organized into a magnificent and intricate network known as the cosmic web. It is a structure of staggering beauty and scale, a luminous, three-dimensional tapestry that fills the entire observable universe. This web is composed of immense, interconnected filaments of galaxies, and as we will discover, dark matter, stretching for hundreds of millions of light-years. These filaments are the great highways of the cosmos, glowing threads of matter that weave their way through the void. Where these shimmering filaments intersect, we find the dense, bright nodes of the web, the great superclusters like Laniakea, the cosmic cities teeming with thousands of galaxies. The filaments themselves are lined with smaller groups and individual galaxies, like towns and villages strung along a country road. And in between this vast, interconnected structure lie the great cosmic voids. These are colossal, almost empty bubbles of space, some of them hundreds of millions of light years in diameter, containing very few galaxies at all. They are the great, dark, silent wildernesses of the universe. To look at a map of this large-scale structure is to see a pattern that resembles neurons in a brain, or the intricate branching of a coral reef. It is a design of profound elegance, a physical record of the universe's history, born from the tiniest, most subtle quantum fluctuations in the moments after the Big Bang, which were then stretched and amplified by cosmic expansion over billions of years into the grandest design we can perceive. Our Milky Way is not just an island, but a single house on a single street in a suburban neighborhood, which is itself part of a sprawling, interconnected, and luminous cosmic metropolis of unimaginable size and splendor. And yet, this luminous splendor, this grand cosmic design that we can finally perceive, is in truth a profound illusion. It is not the real structure, but merely the visible foam on the crest of a deep and unseen cosmic ocean. For the entire story of our journey so far, from the edge of our atmosphere to the filaments of the cosmic web, has been a tour of only the things that shine, the matter that interacts with light. But for nearly a century, astronomers have been haunted by ghosts in the machine, by gravitational effects that can only be explained by the presence of a universe that is almost entirely invisible. This hidden cosmos is dominated by two of the greatest mysteries in all of science: dark matter and dark energy. The first of these specters revealed itself not through what was seen, but through what was missing. In the 1970s, a determined and meticulous American astronomer named Vera Rubin, along with her colleague Kent Ford, was studying the rotation of spiral galaxies, much like our own and the great Andromeda galaxy. The laws of gravity, as laid down by Isaac Newton, make a clear prediction about how such a system should behave. Just as the planets in our solar system orbit the sun more slowly the farther out they are, so too should the stars in a galaxy. The vast majority of a galaxy's visible luminous matter, the stars and gas, is concentrated in its central regions. Therefore, stars on the outer edge of the galactic disk should feel a weaker gravitational pull and should be moving much more slowly than stars near the bright, dense core. But this is not what Vera Rubin found. Her painstaking observations, night after night, revealed a shocking and inexplicable fact. The stars on the very fringes of the galaxies she studied were moving just as fast as the stars much farther in. This flat rotation curve was a flagrant violation of the laws of physics as they were understood. The galaxies were spinning so fast that, based on the gravity of the stars she could see, they should be flying apart, their outer stars flung off into the intergalactic void like water from a spinning wheel. The only way these galaxies could remain bound together was if they contained vastly more mass than could be accounted for by their stars. This mass had to be there, its gravitational influence holding the galaxy together. But it was completely invisible. It emitted no light, no radio waves, no radiation of any kind. It was, for all intents and purposes, dark. This was the smoking gun for the existence of what came to be called dark matter. The idea itself was not entirely new. As far back as the 1930s, a brilliant and eccentric Swiss astronomer named Fritz Zwicky had been studying the Coma cluster, a massive swarm of over 1,000 galaxies. He noticed that the individual galaxies within the cluster were moving about at tremendous speeds, far too fast for the gravity of the cluster's visible matter to keep them from escaping. He concluded that the cluster must be filled with a huge amount of unseen dunkel materia, or dark matter, to provide the necessary gravitational glue. For decades, his work was largely dismissed as a curiosity. But Vera Rubin's work on individual galaxies demonstrated that this was not a quirk of galaxy clusters, but a fundamental property of the universe. We now know that every galaxy, including our own Milky Way, is embedded within a vast, spherical halo of this mysterious, dark matter. A silent, invisible scaffold that outweighs all the visible stars and gas by a factor of at least 5 to 1. Further evidence has poured in from other cosmic phenomena. One of the most powerful tools is gravitational lensing, a prediction of Einstein's theory of general relativity. A massive object, like a galaxy cluster, warps the fabric of space-time around it, and this warped space acts like a lens, bending and magnifying the light from more distant objects that passes through it. By studying the distorted, smeared, and magnified images of background galaxies, astronomers can create a map of all the mass in the foreground cluster, both visible and invisible. These maps confirm, time and again, that the vast majority of the mass in these clusters, the source of most of the gravity, is completely dark. The most spectacular proof of all comes from the Bullet cluster, which is actually 2 galaxy clusters that have passed through each other in a colossal cosmic collision. The hot, ordinary gas of the 2 clusters, which makes up most of their visible matter, smashed into itself and slowed down, remaining near the center of the collision. The dark matter, however, which does not interact with ordinary matter or itself except through gravity, appears to have passed through the collision like a ghost, with the 2 vast halos of dark matter now located on either side of the hot gas. We can see the gas in X-rays, and we can map the dark matter's location through gravitational lensing. The clear separation of the 2 is the most direct evidence we have that dark matter is real, and that it is a fundamentally different kind of substance from the atoms that make up our world. If dark matter was the ghost that held the universe together, the second great mystery was the phantom that is pushing it apart. For most of the 20th century, the biggest question in cosmology was the ultimate fate of the universe. We knew since the work of Edwin Hubble that the universe was expanding, with galaxies rushing away from each other. Gravity, the force exerted by all the matter, both visible and dark, should be acting as a brake on this expansion, slowing it down over cosmic time. The question was there enough matter to eventually halt the expansion and cause the universe to collapse back on itself in a big crunch? Or would the expansion simply slow down forever, leading to a cold, dark, and empty future? To answer this question, two independent teams of astronomers in the 1990s embarked on a monumental project. They planned to measure the rate of cosmic expansion deep in the past by using a special kind of exploding star, a Type 1, a supernova, as a standard candle. These supernovae are the result of a white dwarf star in a binary system accreting matter from its companion until it reaches a precise critical mass, at which point it ignites in a thermonuclear explosion of spectacular and, crucially, uniform brightness. Because their true brightness is known, they can be used as cosmic lighthouses. The dimmer they appear to us, the farther away they must be. Both teams, the Supernova Cosmology Project and the High Z Supernova Search Team, painstakingly scanned the skies, found dozens of these distant explosions, and measured their brightness and redshift to determine their distance and how fast they were receding. But when the results came in 1998, they were astonishing, and at first, unbelievable. The most distant supernovae were consistently dimmer than they should have been in any universe that was slowing down. They were farther away than predicted. The only way this could be possible was if the expansion of the universe was not slowing down at all. In fact, it was speeding up. This was a discovery that shook the foundations of cosmology. Some unknown force, a kind of cosmic anti-gravity, was at work in the universe, overwhelming the pull of all the matter and accelerating the expansion of space-time itself. This mysterious influence was given the name dark energy. Its nature is even more of a mystery than dark matter. It appears to be a property of the vacuum of space itself, a uniform energy density that is constant everywhere. As space expands, more space is created, and thus more of this repulsive dark energy comes into existence, causing the expansion to accelerate even faster. It is a concept that a younger Albert Einstein had once toyed with, adding a cosmological constant to his equations to create a static universe, a move he later called his biggest blunder. Now, it seems he may have been more right than he knew. This accelerating expansion paints a strange and lonely picture for the far future, a big rip or big freeze, where galaxies are pushed apart so fast that eventually the light from all other galaxies will be stretched beyond our horizon, leaving our own Milky Way, or its merged remnant, Milkomeda, as a solitary island in an endless, empty, and dark void. When we finally tally the cosmic budget, putting together everything we have learned, the result is deeply humbling. The universe, it turns out, is composed of roughly 68% dark energy, the mysterious force driving the acceleration. About 27% is dark matter, the invisible scaffolding upon which the galaxies are built. That leaves a mere 5% for everything else, for all the ordinary, atomic, baryonic matter that makes up every star you have ever seen, every planet we have ever discovered, every nebula, every human being, every book, and every idea. The grand, luminous, and magnificent cosmos we have been exploring is nothing more than a tiny, shimmering decoration on a vast and profoundly invisible reality. This strange and humbling cosmic inventory, with its vast, invisible majority, was not established at the dawn of time, but is instead the result of a colossal 14 billion-year story of cosmic evolution. To understand how our universe came to be, we must embark on the ultimate journey, back in time, rewinding the cosmic clock past the first galaxies and the first stars, past the formation of the first atoms, and into the very first moments of existence itself. Our journey takes us back some 13.8 billion years, to a point before which time and space, as we know them, did not exist. Our current laws of physics cannot fully describe this initial state, but they point to a condition of unimaginable heat and infinite density, a point from which everything, all the matter and energy, and even the fabric of space-time, would spring. This is the moment we call the Big Bang. It was not an explosion in space, but an explosion of space itself. A rapid, hot expansion from a single point that marked the beginning of everything. In the very first, tiniest fraction of a second, the universe was a maelstrom of energy so intense that the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified into a single primordial superforce. In an instant so brief, it is almost incomprehensible, lasting from perhaps 1/100th of a billionth of a billionth of a billionth of a second after the beginning. The young universe underwent a period of breathtakingly rapid expansion known as cosmic inflation. Driven by a type of energy that is now long gone, the universe swelled in size exponentially, expanding from smaller than an atom to larger than a grapefruit in a sliver of time. This hyper-expansion was the event that set the stage for the cosmos we see today. It smoothed out any initial wrinkles or irregularities in the fabric of space-time, resulting in the vast, uniform, and geometrically flat universe we now observe. And critically, during this period, tiny, random quantum fluctuations, the inherent jitteriness of energy on the smallest scales, were stretched to enormous, macroscopic sizes. These slight variations in density, minuscule seeds of structure planted in the first moments of time, would later grow under the influence of gravity to become the great clusters of galaxies and the vast cosmic voids, the very architecture of the cosmic web. Once this inflationary period ended, its energy was converted into a seething, hot soup of fundamental particles, a roiling quark-gluon plasma at a temperature of many trillions of degrees Celsius, or trillions of degrees Fahrenheit. And the more stately, steady expansion we see today began. The universe was now a blistering, opaque fog of matter and radiation, so hot and dense that protons and neutrons could not yet exist as stable particles. As the universe continued to expand, it cooled. And as it cooled, it crossed a series of critical thresholds. About 1 microsecond after the Big Bang, the universe had cooled enough for quarks to bind together, forming the first stable protons and neutrons, the building blocks of atomic nuclei. It was in this moment that one of the deepest mysteries of our existence was resolved. For every particle of matter, physics tells us there should be an equal and opposite particle of antimatter. When they meet, they annihilate each other in a flash of pure energy. In the primordial furnace, pairs of matter and antimatter particles were constantly being created and destroyed. But for some reason that we still do not fully understand, a tiny imbalance occurred. For every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter. As the universe cooled, the annihilations continued until all the antimatter was gone, leaving behind that tiny 1 in a billion surplus of matter. That small leftover fraction is what constitutes everything we see today. Every star, every planet, and every living thing is a relic of this primordial asymmetry, a survivor of the great war between matter and antimatter. For the next few minutes, the entire universe was a nuclear reactor. Between the first second and about the third minute, the cosmos was hot and dense enough for a process called Big Bang nucleosynthesis to occur. Protons and neutrons fused together to forge the nuclei of the lightest elements. By the time this process was over, the primordial chemical composition of the universe had been set. About 75% of the atomic matter was hydrogen. About 25% was helium, along with trace amounts of lithium. Every other element on the periodic table, the carbon in our bodies, the oxygen we breathe, the iron in our blood, had yet to be created. They would have to wait for the hearts of stars that did not yet exist. For the next 380,000 years, the universe remained a hot, opaque fog. The light elements were there, but it was still too hot for electrons to be captured by the atomic nuclei. They remained free, and this sea of free electrons acted as a perfect screen, scattering photons of light so that they could not travel far. The universe was like being inside an incredibly bright, dense cloud. But as the expansion continued, the temperature of the cosmos finally dropped to about 3,000 degrees Celsius, or about 5,400 degrees Fahrenheit, a temperature similar to the surface of a cool star. At this point, it was no longer hot enough to keep the electrons and nuclei apart. Electrons were captured into stable orbits, forming the first neutral atoms of hydrogen and helium. This event is called recombination, and it changed everything. With the free electrons now bound into atoms, the universe suddenly became transparent. The photons of light, which had been trapped in the cosmic fog, were now free to travel unimpeded through space for the first time. The universe, in an instant, became see-through. This ancient, freed light is what we detect today as the cosmic microwave background radiation, the faint afterglow of creation, a baby picture of the universe when it was just a few 100,000 years old. But this moment of first light also marked the beginning of a new epoch, the cosmic dark ages. The universe was now filled with vast, dark, and silent clouds of neutral hydrogen and helium gas, with no stars to illuminate them. The only light was the fading glow of the Big Bang, now stretched and redshifted beyond the visible spectrum. For hundreds of millions of years, the universe was a place of profound darkness, a vast and patient quiet, as gravity slowly and silently went to work, pulling on those tiny density variations left over from inflation, gathering the densest clumps of gas and dark matter together, patiently building the stage for the next and most brilliant act of the cosmic drama, the ignition of the very first stars. That brilliant act, the ignition of the first stars, would illuminate the cosmos for billions of years before a spark of a different kind was kindled on a small, rocky planet orbiting an unremarkable yellow star. Here, the universe had not only produced life, but a form of life capable of looking up at the star-dusted night and wondering not just what it was, but how one might get there. For millennia, this was a question for myth and fantasy, a dream of celestial chariots and wings of wax. But in the late 19th and early 20th centuries, in the quiet studies and makeshift workshops of a few brilliant and isolated visionaries, the dream began to take on the rigor of science. In a provincial Russian town, a nearly deaf schoolteacher named Konstantin Tsiolkovsky, inspired by the tales of Jules Verne, meticulously worked out the fundamental principles of rocketry. He never built a rocket himself, but in 1903, he published what is now known as the Tsiolkovsky rocket equation, the mathematical bedrock upon which all spaceflight is built. He envisioned liquid-fueled, multi-stage rockets, space stations, and the colonization of the solar system, all while living a life of profound obscurity. At the same time, in the United States, a quiet and secretive physicist named Robert Goddard was independently reaching similar conclusions, but he was a tinkerer as well as a theorist. In 1926, on a cold March day in a Massachusetts cabbage patch, he launched the world's first liquid-fueled rocket. It flew for only 2.5 seconds, reaching an altitude of just 12 meters, or about 41 feet. But it was a leap as significant in its own way as the first flight of the Wright brothers. And in Germany, the physicist Hermann Oberth published his own influential works on space travel, inspiring a generation of young enthusiasts who formed amateur rocket clubs, dreaming of a future among the stars. These early, optimistic dreams, however, were destined to be forged into reality in the fires of global conflict. One of Hermann Oberth's most brilliant protégés was a young German aristocrat named Wernher von Braun, a man who possessed a singular genius for engineering and an unyielding ambition to build rockets that could reach space. In the 1930s and 40s, his ambition found a patron in the Nazi regime, which saw in rocketry not a tool for exploration, but a revolutionary new weapon of war. Von Braun and his team were given immense resources, and at a secret facility on the Baltic coast called Peenemünde, they developed the world's first long-range ballistic missile. It was called the Aggregat 4, or A4, but it would become infamous under its propaganda name, the Vergeltungswaffe 2, or V2, meaning Vengeance Weapon 2. This was a technological marvel of its time, a 14-meter or 46-foot tall liquid-fueled rocket that could carry a 1,000-kilogram or 2,200-pound warhead over 300 kilometers, or about 190 miles. It was the first man-made object to cross the boundary of space, reaching altitudes of over 80 kilometers, or 50 miles, on its ballistic trajectory. But its purpose was terror, and thousands of these weapons were launched at cities like London and Antwerp in the final stages of the Second World War. When the war ended, this terrifying but revolutionary technology and the engineers who created it became the spoils of victory. In a coordinated intelligence program called Operation Paperclip, the United States secretly recruited von Braun and over 100 of his top scientists, bringing them and the captured V2 hardware to America. The Soviet Union, for its part, captured other German technicians and rocket production facilities, setting the stage for a new kind of conflict, a Cold War in which the ultimate high ground was not a hill on a battlefield, but outer space itself. The starting pistol for this new race was fired on the 4th of October, 1957. On that day, the Soviet Union, to the utter shock and astonishment of the world, launched Sputnik 1, the first artificial satellite, into orbit around the Earth. It was a simple object, a polished metal sphere just 58 centimeters, or 23 inches, in diameter, with 4 long antennas. It carried no complex instruments, only a simple radio transmitter that broadcast a steady, hypnotic beep, beep, beep signal that could be picked up by amateur radio operators around the globe. This small, orbiting sphere was a political and psychological earthquake. It demonstrated a technological prowess that the United States did not believe the Soviets possessed, and it carried a terrifying implication. If they could put a satellite into orbit, they could certainly launch a nuclear warhead at any city on Earth. America was thrown into a state of crisis, its sense of technological superiority shattered. The immediate response was the creation of a new civilian agency to manage the nation's space efforts, the National Aeronautics and Space Administration, or NASA, in 1958. But the Soviets continued their string of spectacular firsts. A month after Sputnik 1, they launched Sputnik 2, carrying the first living creature to orbit the Earth, a dog named Laika. Then, on the 12th of April, 1961, they achieved the ultimate triumph. A 27-year-old Soviet cosmonaut named Yuri Gagarin was strapped into his Vostok 1 capsule and launched into orbit, becoming the first human being to ever leave the planet and see it from space. His single orbit of the Earth, lasting 108 minutes, made him a global hero and cemented the Soviet Union's dominance in the early years of the space age. The United States followed just weeks later with the suborbital flight of Alan Shepard, a heroic and important step for the Mercury program. But it was a clear second place in the race for human spaceflight. Faced with this series of defeats, the young American president, John F. Kennedy, understood that simply catching up would not be enough. The United States had to make a leap so bold, so audacious, that it would redefine the race entirely. On the 25th of May, 1961, in a speech before Congress, he committed the nation to achieving a staggering goal. Before this decade is out, of landing a man on the moon and returning him safely to the Earth. At the time, this was a goal that bordered on science fiction. The United States had a total of just 15 minutes of human spaceflight experience, and the technological challenges of a lunar mission were immense. But the challenge was accepted, and it galvanized the nation. The Apollo program became a monumental national effort, at its peak employing over 400,000 people and consuming nearly 4% of the federal budget. The key to the mission was the development of a rocket powerful enough for the journey, the Saturn V. Standing over 110 meters, or 363 feet, tall, it was the masterpiece of Wernher von Braun and his team of former V-2 engineers, a direct and colossal descendant of their wartime weapon, now repurposed for this peaceful, ambitious quest. After years of testing, tragedy, and triumph, on the 16th of July, 1969, a Saturn V rocket thundered into the sky, carrying the crew of Apollo 11. 4 days later, on the 20th of July, the lunar module Eagle, with Neil Armstrong and Buzz Aldrin aboard, touched down on the tranquil, dusty plains of the moon's sea of tranquility. As hundreds of millions of people on Earth watched in awe on grainy television screens, Armstrong descended the ladder and spoke the immortal words, "That's one small step for a man, one giant leap for mankind." In that moment, a dream as old as human consciousness was realized. For the first time, a living being from Earth had walked upon another world, a profound and triumphant culmination of humanity's long, slow ascent to the stars. The giant leap to the moon was a profound human and political victory. But it was, in a very real sense, the end of the beginning. The Apollo era was driven by a geopolitical imperative that could not be sustained indefinitely. After 6 crewed landings, the program was canceled in the early 1970s, and humanity's brief golden age of crewed deep space exploration drew to a close. The focus shifted from grand voyages to building permanent infrastructure in low Earth orbit, leading to the American Skylab station, the Soviet Salyut and Mir programs, and eventually the collaborative triumph of the International Space Station. But while human astronauts remained tethered to the immediate vicinity of our planet, a new generation of explorers was just beginning its far more extensive journey. These new explorers were not human, but robotic, a tireless and ever more sophisticated army of probes, rovers, and most importantly, space telescopes designed to extend our senses, our curiosity, and our intellect to the farthest reaches of the cosmos. Chief among these new explorers, and arguably the most revolutionary scientific instrument ever built, is the Hubble Space Telescope. Launched into orbit in 1990, Hubble had a specific and crucial advantage. By operating from a vantage point 540 kilometers, or 335 miles, above the surface, it could see the universe free from the blurring, distorting effects of Earth's atmosphere. This gave it a clarity of vision that no ground-based telescope could ever match. Its initial deployment, however, was a near catastrophe. A flaw in the shape of its primary mirror, no wider than a fraction of a human hair, rendered its images disappointingly fuzzy. But thanks to a heroic and ingenious shuttle servicing mission in 1993, which installed corrective optics, Hubble's true potential was unleashed. For over 3 decades, it has poured down a torrent of iconic images and paradigm-shifting discoveries. It helped to pin down the Yesod of the universe at 13.8 billion years and provided crucial data that confirmed the universe's expansion is accelerating. Hubble gave us conclusive evidence that supermassive black holes reside at the center of nearly every major galaxy, including our own. It has photographed the birth of stars in the majestic, glowing pillars of the Eagle Nebula, and studied the beautiful, intricate death shrouds of sun-like stars in planetary nebulae. It has charted the weather on our neighboring planets, discovered new moons around Pluto, and for the first time directly measured the chemical composition of the atmosphere of a planet orbiting another star. An exoplanet named HD 209458b. Perhaps its most profound contribution was an experiment born of a magnificent gamble. In 1995, astronomers pointed the telescope at a tiny, completely black, and seemingly empty patch of sky for 10 consecutive days, collecting every last photon of light. The result was the Hubble Deep Field, a stunning cosmic tapestry containing over 3,000 galaxies, some of them seen as they were when the universe was less than 1 billion years old. This and subsequent, even deeper observations, like the ultra-deep field, fundamentally changed our view of the cosmos, revealing it to be far more crowded and ancient than we ever imagined. If Hubble was the instrument that opened our eyes to the vastness of the cosmos, its successor, the James Webb Space Telescope, was designed to reveal its origins. Launched on Christmas Day in 2021, the Webb is a technological marvel, the largest and most powerful space observatory ever built. Its primary mirror, a giant honeycomb of 18 gold-plated hexagonal segments, is over 6 times larger in area than Hubble's, giving it far greater light-gathering power. But its true advantage is its sensitivity to infrared light. While Hubble was optimized for visible and ultraviolet light, Webb is designed to see the universe in the longer wavelengths of the infrared spectrum. This allows it to do 2 things Hubble cannot. First, it can peer through the dense clouds of cosmic gas and dust that obscure the view of stellar nurseries and the cores of galaxies, revealing the processes of star and planet formation hidden within. Second, and most importantly, it can see farther back in time than any instrument before it. Because the universe is expanding, the light from the most distant objects is stretched to longer, redder wavelengths as it travels across space, a phenomenon known as cosmological redshift. The very first stars and galaxies that ignited in the cosmic dawn are so distant that their light has been stretched all the way into the infrared. Webb, with its giant mirror and advanced infrared detectors, is a time machine specifically built to capture this faint, ancient light. From its lonely orbital perch, 1.5 million kilometers, or about 1 million miles, from Earth, a position that keeps it cold and shielded from our planet's heat, Webb has already begun to revolutionize astronomy. It has discovered some of the most distant galaxies ever seen, pushing our cosmic frontier back to just a few 100 million years after the Big Bang. It has found some of these early galaxies to be far more massive and mature than our theories predicted, calling into question our understanding of how the first cosmic structures formed. It has provided the most detailed views ever of exoplanet atmospheres, discovering methane and carbon dioxide on a potential Hycean world, a planet with a hydrogen-rich atmosphere and a liquid water ocean. It has even given us stunning new images of the planets in our own solar system, from the faint rings of Jupiter to the turbulent storms on Neptune. Webb and Hubble are not rivals, but partners. Together, they provide a multi-wavelength view of the universe, with Webb's deep infrared vision complementing Hubble's sharp observations in the visible and ultraviolet. While these great observatories look out upon the grandest scales, other robotic explorers have been engaged in a more intimate, hands-on form of exploration. Nowhere has this been more true than on the planet Mars. Since the first successful flyby by Mariner 4 in 1965, a steady stream of orbiters, landers, and rovers has been sent to the red planet, slowly peeling back its secrets. The Viking landers of the 1970s conducted the first, and still controversial, experiments to search for life in the Martian soil. In the late 1990s, the Sojourner rover became the first wheeled vehicle to explore another planet, followed by the much larger and more capable twin rovers, Spirit and Opportunity, which roamed for years, providing definitive proof of Mars's ancient, watery past. More recently, the car-sized Curiosity rover, a mobile chemistry lab, has been analyzing the rocks of Gale Crater, confirming that the planet once had all the necessary chemical ingredients for life. It has now been joined by the Perseverance rover, which is actively collecting and caching the most promising rock samples for a future highly ambitious mission to retrieve them and bring them back to Earth for analysis in our most advanced laboratories. This robotic armada, both in orbit and on the surface, is not just exploring Mars, but is also scouting for the day when human footprints will finally follow the tracks of our robotic pioneers. This relentless and multifaceted exploration, from the grand cosmic vistas of Webb to the dusty plains of Mars, represents a new golden age of discovery, an era where our reach is limited not by the speed of a rocket, but only by the power of our curiosity and the ingenuity of our machines. Yet for all the ingenuity of our machines, their journey into the cosmos is guided by a framework born not of physics or engineering, but of human ideals, a framework of law and lore designed to govern our behavior in this vast new arena. The very idea seems paradoxical. How could a realm so boundless, so seemingly empty and lawless, be subject to treaties and traditions? But as humanity took its first tentative steps into orbit, it became terrifyingly clear that the conflicts of Earth could all too easily follow us into the heavens. The space race was born of the Cold War, a rivalry between two superpowers, the United States and the Soviet Union, armed with nuclear arsenals capable of ending civilization. The prospect of this rivalry extending into space, with orbiting weapons platforms and military bases on the moon, was not science fiction. It was a real and terrifying possibility. It was in this climate of existential threat that diplomats and scientists achieved something remarkable. In 1967, after years of careful negotiation, the world's nations came together to sign the cornerstone of space law, a document whose full title is as grand as its ambition: the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, including the Moon and other celestial bodies. Known simply as the Outer Space Treaty, it is a document of profound and almost utopian optimism. It declared, in no uncertain terms, that outer space was not for sale. It could not be subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. No one could own the moon. Furthermore, it established space as the province of all mankind, a shared commons to be explored freely and peacefully by all. Its most critical provision was a ban on placing nuclear weapons or any other weapons of mass destruction in orbit, on celestial bodies, or in space in any other manner. At the height of a global ideological struggle, humanity collectively decided to set aside its greatest frontier as a sanctuary for peace and cooperation. This treaty, for all its idealism, was also a deeply practical document. It established that nations were responsible and liable for the objects they launched into space, meaning a country could not simply disavow a satellite that malfunctioned and crashed in foreign territory. It also enshrined the idea that astronauts were to be regarded as envoys of mankind, and that all states should render them all possible assistance in the event of an accident or emergency landing. Yet the treaty was a product of its time, and its elegant principles now face the complex realities of a new space age it could never have fully envisioned. The Peaceful Purposes Clause, for instance, has always existed in a state of delicate ambiguity. While weapons of mass destruction are banned, the treaty does not forbid military activities altogether. The use of satellites for reconnaissance, communication, and navigation has been a cornerstone of military operations for decades, a use that is generally accepted as non-aggressive. The greatest challenge, however, comes not from nations, but from the burgeoning private commercialization of space. The treaty was written for a world where only two superpowers had spacefaring capabilities. It says nothing about private companies like SpaceX or Blue Origin, or the prospect of asteroid mining and the ownership of celestial resources. Legal scholars now fiercely debate whether a private company can extract and own valuable minerals from an asteroid, even if the asteroid itself cannot be claimed by a nation. This has led to new agreements, like the Artemis Accords, which attempt to build upon the principles of the Outer Space Treaty for a new era of commercial and international partnerships. The law of space is therefore not a static relic, but a living, evolving body of principles, constantly being reinterpreted as our reach into the cosmos expands and our ambitions grow more complex. But the human relationship with space has always been about more than just legal frameworks and technological achievements. As soon as we were able to see our planet from the outside, our perspective on everything began to change. This profound cognitive shift, experienced by nearly every astronaut who has seen the Earth from orbit or from the Moon, is known as the overview effect. From the vantage point of space, the intricate, colorful, and living sphere of Earth hangs in a vast, silent darkness. Borders, nations, and the conflicts that define them are completely invisible. All that can be seen is a single, unified, and breathtakingly fragile planetary system. Astronauts have spoken of an overwhelming sense of connection, of the realization that everything we have ever known, every joy, every sorrow, every war, and every work of art took place on that one small, suspended globe. This perspective, brought back to Earth through their stories and photographs, had a powerful and transformative impact on the human psyche. The iconic image of Earthrise, taken by the crew of Apollo 8 in 1968, the first humans to orbit the Moon, showed our blue marble rising above the stark, lifeless lunar horizon. It became a symbol of unity and fragility, and it is often credited with helping to galvanize the modern environmental movement. A generation later, another image cemented this cosmic perspective. In 1990, as the Voyager 1 spacecraft was about to leave the solar system, the astronomer Carl Sagan persuaded NASA to turn its camera around one last time to take a final portrait of the worlds it was leaving behind. From a distance of 6 billion kilometers, or nearly 4 billion miles, Earth appeared as a single, tiny pixel, a mote of dust caught in a sunbeam. Sagan immortalized this image as the pale blue dot, a humbling reminder of our place in the cosmos and a powerful argument for our shared responsibility to care for our only home. This cosmic perspective, this blend of awe, humility, and wonder, has made space the ultimate muse. For as long as we have looked up, the cosmos has fueled our art, our music, and our stories. The lore of the cosmos began with mythologies, with constellations named for heroes and gods, and planets that were divine messengers. But as science gave us a new understanding, the inspiration did not fade. It deepened. The cold, majestic grandeur of space has been translated into the sweeping orchestral movements of Gustav Holst's The Planets and the ambient, ethereal soundscapes of Brian Eno. It fueled the psychedelic odysseys of David Bowie's Space Oddity and Elton John's Rocket Man. The visual spectacle of space has been a constant wellspring for cinema, from the whimsical silent film A Trip to the Moon in 1902 to the philosophical, mind-bending journey of Stanley Kubrick's 2001 A Space Odyssey. A film so visionary, it was released a year before humanity had even landed on the moon. And literature, in the form of science fiction, has consistently been both a reflection of our current relationship with space and a powerful engine for its future. The dreams of Jules Verne and H.G. Wells inspired the first generation of rocket scientists, creating a powerful feedback loop where imagination ignites the desire for exploration. And exploration, in turn, provides new fuel for the imagination. The legal and the cultural are two sides of the same human coin. The Outer Space Treaty created a peaceful canvas, a framework that set the cosmos apart from our terrestrial squabbles. And upon that canvas, we have projected our deepest fears, our greatest hopes, and our most profound sense of beauty, creating a rich and growing body of lore that tells the story not just of where we are going, but of who we are. And so we find that our journey into outer space is ultimately a journey into ourselves. This projection of our laws, our art, and our deepest questions onto the cosmic canvas is the final, most intimate layer of the story. Our voyage began just 100 kilometers, a mere 62 miles, above the familiar ground, where we crossed an invisible line and the sky gave way to the void. Yet we discovered this void was not empty, but a dynamic realm filled with the sun's breath, the faint, residual heat of creation, and the ghosts of particles passing through us. We toured our own cosmic neighborhood, a place of stunning diversity, from the scorched, cratered plains of Mercury to the crushing, hellish atmosphere of Venus. We saw the ghosts of ancient rivers on the red deserts of Mars, flew through the majestic rings of Saturn, and ventured into the deep, frozen twilight of the Kuiper Belt, the home of Pluto and the icy remnants of our own solar system's birth. From there, we took the immense leap into interstellar space, adopting the light year as our new measure for a cosmos of unimaginable scale. We found our sun to be just one of hundreds of billions of stars in our home, the Milky Way galaxy, a vast, swirling city of stars, gas, and dust. But even this grand structure was revealed to be a single island in an archipelago of countless others. We learned how Edwin Hubble, with a single observation, expanded the universe, revealing a cosmos filled with galaxies organized by gravity into groups, clusters, and immense superclusters. And on the grandest scale of all, we saw the breathtaking architecture of the cosmic web, a luminous, interconnected tapestry of galactic filaments stretching across billions of light years, the largest structure in existence. This entire visible journey, however, was but a glimpse of the true reality. For we then confronted the great cosmic mysteries of the dark, the invisible dark matter that holds the galaxies together, and the even more enigmatic dark energy that is pushing the universe apart at an ever-accelerating rate, revealing that everything we can see is but a tiny fraction of what truly is. With this new, humbling inventory in hand, we traveled back in time, rewinding the cosmic clock 13.8 billion years to the very beginning, to a point of infinite heat and density from which all of space, time, and matter erupted. We followed the story of the universe's first seconds, through the forge of the first elements, until the cosmos cooled enough to become transparent, releasing the ancient light that we can still see today. After an era of darkness, we witnessed the dawn of the first stars, and billions of years later, the dawn of a new kind of exploration, as humanity, driven by conflict and curiosity, finally broke the bonds of Earth. From the first tentative beep of Sputnik to the giant leap of the Apollo astronauts, we ascended into space, only to turn around and see our own planet for the first time, a single, fragile, and unified world, a pale blue dot suspended in the vastness. The story of outer space, therefore, has no true conclusion. It is a narrative that is still being written, with every new observation from telescopes like Hubble and Webb, and every new robotic explorer on Mars adding another page. We have learned that our universe is vast, ancient, largely invisible, and governed by laws of profound elegance. But perhaps the most extraordinary discovery of all is that a small part of this universe, the thinking dust on a single small planet, has become capable of piecing this story together. The quest for knowledge, the insatiable need to explore the next frontier and understand our place within the grand design, is an intrinsic part of our nature. It is an endless journey, not to a final destination, but towards an ever-expanding horizon of wonder, a voyage that will continue as long as we have the courage to look up and ask what lies beyond.